All right, good morning, ladies and gentlemen. Let's get started. So on, today's Tuesday, last Thursday, we got to thinking about capillary fluid flux. So we got to thinking about capillaries as volume regulators. Okay, so that's what they're going to do for us in terms of our quest to understand the regulation of mean arterial pressure. It's dark back there. That's not right. There we go. So we looked at then the pressures that are going to change flux across a capillary bed. Okay, and essentially they broke down to hydrostatic pressures versus osmotic pressures. Okay, hydrostatic pressures we saw were the primary driving force for fluid to move from the capillary compartment into the interstitial space. And then we saw osmotic pressures were the primary driving force for moving fluid from the interstitial space back into the capillaries, because that blood compartment is more concentrated, right? So then, if we've got these two forces in either direction, which way fluid is going to move will then be dictated by which pressure is greater. Okay? So we got ourselves to thinking about, really, the game afoot is delta P greater than delta pi? Because if that's true, then we're going to get net flux from the capillaries to the interstitial space. All right, if delta pi is greater than delta P, then we're going to get net fluid flux from the interstitial space back to the capillaries. Where they're equal, we get no net flux. There's flux, but we get no net flux. All right? So there was an equation that we put up to show how that relationship would be derived. And then we built a tool, knowing that capillary pressure, which was one of the primary driving hydrostatic pressures in delta P, would actually have to change over the length of a capillary bed. So we had to acknowledge that happening, okay? Because there has to be flow across a capillary bed. Then our PC, pressure in the capillary, would have to drop across the capillary bed, which means our delta P then has to drop across the capillary bed. Okay, so then if our delta P drops as we move across the capillary bed, and our delta pi stays the same, then we saw that there would indeed be places along that capillary where we would have delta P greater than delta pi. Okay, so net filtration from the blood space into the interstitial space. There would be a spot along the capillary bed where both of those forces were equal, so flux but no net flux. Okay. And then a region over the length of the capillary where we would get delta pi being greater than delta P. So the forces to move fluid from the interstitial space to the capillaries is greater than the reverse. So we're going to get what we call absorption or reabsorption. Okay, so across an entire capillary bed, we saw that indeed we would get filtration over a certain length of that and reabsorption over a certain length of that. Okay, so that's what this tool was. And we will come back to using this tool in a minute, because we still have a problem, and that is that we filter over a longer length of the capillary bed than we reabsorb, which means we spend more time at any capillary bed filtering than we do reabsorbing. Okay, that means we spend more time moving fluid from the blood space into the tissues than we do back. Okay, so this is problematic, because that means we are constantly moving more volume from our blood into our tissues than we're moving back. And this flux, this difference between filtration and reabsorption, was actually to the tune of about 3 liters a day, right? So that means that you're moving 3 liters a day more from your blood compartment to the interstitial space than you are backwards, right? Which means we should actually be blowing up, right? We should actually be having all kinds of edema, all kinds of fluid on the tissues, right? And the crazy thing is across any given day, you're moving 3 extra liters, but you only have 5.5 liters of blood in the first place. Right, so after 1 day, you should only have 2.5 liters of blood left in the system if we are not returning it back. Okay, so before we flex our muscle using this filtration reabsorption tool, we're going to have to get that volume back. Okay, so we have to spend a little time thinking about the lymphatic system. Okay, so that's why we're headed there next. Our fourth compartment that we do need to think about is our lymphatics. Okay, so what are these? These are going to be a blind-ended tube, they call them, a closed-ended network of tubes that originate in the tissue. Okay, so this is not a circulatory system like we've been talking about. This tube actually starts at the level of the tissue and then will work its way to joining the vasculature somewhere along the line. Okay, it's not something that we circulate like arteries, arterioles, capillaries, veins back to the heart. Okay, not a circulatory system, starting at the level of the tissue. And essentially, it picks up filtrate and the protein leak. So any proteins that come across from the blood into the interstitial space, then we can pick up that protein leak, and especially that filtrate, so that 3 liters of extra filtrate that we get per day, and deliver it back into the blood compartment. We have to get it there, okay? It's a highly permeable set of tubes, and then this system is going to drain. We're going to have the tubes start very small at the level of the tissue, and then converge into larger lymphatic vessels, which will then converge with the vasculature right back near the right atria. Okay, so we're going to plug this system right back into the right atria, all right? So think about where we're going. We're going back into the low pressure side of the system. Okay, critical that we didn't plug this lymphatics into the left ventricle, right? We would have all kinds of pressure problems, so really critical. We're taking this system and plugging it back into the low pressure side of our vasculature, right? So essentially, where were we? We were thinking about, let's say, a capillary. Let's draw where we are relative to the discussion we just had. Let's say we've got this capillary moving through a tissue. So if this is our capillary and we've got our blood flow in this direction, and this is our interstitial space, and then so we have our lymphatic vessels starting in that interstitial space. So we have just talked about how along the length of any given capillary, we were going to have a region at which delta P is greater than delta pi. All right, so we're going to get net movement from the blood compartment into the interstitial space. Okay, and we do that along a fair amount of the capillary. And then there will be spots where delta P is equal to delta pi. Okay, not much. And so that we get net flux. We get no net flux. We do get movement, but no net flux. Okay, because both hydrostatic and oncotic pressures are equal, but opposite. Okay, and then we have a region of that capillary where the oncotic drive to move fluid into the interstitial space is greater than the hydrostatic drive to move volume out, so we get net movement from the interstitial space back into the capillary compartment. Okay, so essentially that's what we've just discussed in that graphic form. Okay, so the question then is with all this filtrate here, that's our extra 3 liters per day. How do we get that back into the vascular compartment? So we have these lymphatic vessels whose walls are made up of endothelial cells, right, with really large, I guess what would be akin to the cleft pores that we've already talked about. So that just means there's quite a few spaces or quite a large space in between these endothelial cells, so we can actually move freely fluid plus proteins into this compartment, right? So how do we get flow to go from the interstitial space into the lymphatic space? Well, you need a pressure drop and low resistance, okay? So it gets us right back to thinking about flow equaling P1 minus P2 over R, okay? So we have a pressure in the tissue that we've been talking about out here, right? A hydrostatic pressure. We have a volume there, so we have a pressure there. And then we're going to have a pressure in the lymph. All right, so if this is PT, pressure in the tissue is P1, and pressure in the lymph is P2. In order for us to get flow in that direction, pressure in the tissue has to be greater than pressure in the lymph, and then we will get flow, okay? So as long as we have pressure in the tissue being greater than pressure in the lymph, we're going to get flow. Okay? So essentially what we need then is for this filtrate to generate a higher pressure in the tissue, so then we're going to get flow through these pores into the lymphatics, right? And then we have to move that. We can't let pressure or volume build up there, or pressure builds up there. So we need to now help encourage volume that we just moved into the lymph to move along its vasculature up towards the atria, the right atria, okay? So there are a couple of ways that this system is built to help encourage that to happen, okay? So if we're going to think about what helps lymph flow, okay, first of all, there are one-way valves, okay? So that means we're going to get directional flow. So lymph vessels have one-way valves, and so that's what these are supposed to represent here. These are really just endothelial cells that head into the part of it into the lumen of the vessel, so that if we could get flow to head up past these, if flow were to occur in the opposite direction, we would close the valve, okay? So if flow were to happen in this direction, we would close the valve, and volume would not be allowed to re-enter that part of the lymphatics. Okay, so now we can actually move volume kind of up in chunks, right? As long as you can get that volume up above the next valve, we don't have to worry about it creating pressure below, okay? So let's just write that idea down. So essentially, if we want flow into the lymph, we said we needed pressure in the tissue being greater than pressure in the lymph. All right, so if we get pressure in the tissue being less than pressure in the lymph, we're going to get backflow in the lymphatic system. Which will result in closing those valves. Okay, so we have a valve system, which is fantastic, but now we need ways to help the lymphatics. We need a way to help that volume or promote that volume to move above different valved areas. Okay, so the valves just aren't here along the tube, that as long as you, when you start to converge these smaller lymphatics into larger lymphatics, there's one here called a collecting lymphatic, then they will all have valves as well. And when the collector lymphatic vessels converge into larger lymphatic vessels, they will have valves as well. Okay, so now we need to promote movement in that direction. So one of the ways that we also do it is through contraction of smooth muscle. So the larger lymphatics actually have, like that little blood vessel, like that little arteriole that we looked at on the video the other day, the larger lymphatic vessels will have smooth muscle cells wrapping circumferentially around the vessels. Okay, so that if I can get, so now we have contractile control. We can actually make the diameter smaller here. I make the diameter smaller here. I might get flow in this direction, but I'm going to close the valve. So I'm going to get flow in this direction where there is no valve or there is an open valve. Okay, so it promotes these valves promote directional movement. So this is now almost like the gut. If we can get the muscle to contract in a kind of a sequential order, then we can actually take this tube and squeeze volume up. Okay, but you have to get the smooth muscle to contract in a sequential order. So it is thought that there are pacemaker cells down here. One of these hypotheses is that down here, I've got this pacemaker cell which will contract or change its membrane potential and pass on that change in membrane potential to a neighboring smooth muscle to get it to contract. And then that change in calcium will affect the neighboring smooth muscle to get it to contract, and so on and so on and so on. Okay, so you can actually get contraction moving in this direction in order to squeeze volume up past the next valve. Okay? So the combination of one-way valves and vasomotion, let's write that down. One-way valve and vasomotion, we should be able to get this thing to move. Okay, so let's just make sure we write that down. That's what's on the top of this guy here. Like that. Okay, where we get that vasomotion. It just says the larger collector lymph vessels are wrapped in smooth muscle, so now they can change their diameter, so they can contract. So the spontaneous idea is that indeed we are seeing suddenly movement at the level of the lymphatics, but not sure what's promoting that movement. So a great spot to get to grad school and try to figure this stuff out. These are very tough vessels to see, but wicked when you see them. They're unbelievable. So there is a thought, so where the spontaneity comes from, obviously it's just not random, something's driving it, we just don't know what it is yet. So we did talk about how there's a possibility of those pacemaker cells. Okay, so that's a possibility. There's a second possibility, and that is that it is just the myogenic response, that when you get stretched, muscles contract. Okay, they're smooth muscle, they have that myogenic response where stretch causes constriction. We saw it in the gut, we talked about it in arterioles. So that when volume does move from one compartment to another above a valve, you're going to stretch that smooth muscle, it's going to contract and propel volume forward. Okay, so it's possible that it is also driven by the myogenic response. But we're not sure. So those are kind of very active ways that we are built in order to help promote lymph flow. But now there are other pressures that help us promote lymph flow, right? So there's transmural pressure to help promote lymph flow. So remember that transmural pressure was the pressure difference between the environment or the tissue acting down on the vessel versus the pressure on the inside, and this would, I guess, be the pressure in the lymph in order to keep that vessel open. Right? So now every time you get muscle contraction, let's say, and you compress this tube, you will help move volume from one compartment up to another valve, through a valve and up to the upper compartment. Okay? So tissue pressure now, or environmental pressure. You're also going to do that every time you press down, let's say on the top of your hand. You're creating that increase in environmental pressure. Okay, you're going to move volume in a direction. If I were to suddenly make this diameter smaller, volume would try to move in that direction because of that transmural pressure, but the valve will close. Right? So volume will move in this direction where a valve is open. So transmural pressure will help us move volume from one valve compartment up to the next. Okay? And then, of course, we've already talked about tissue pressure, how we're going to get flow in the lymph, or flow into the lymph if pressure in the tissue is greater than pressure in the lymph. Okay, and we were working off of our beloved flow equation in order to get that to happen. But there is a maximum effectiveness, okay? So you won't see a linear relationship between increasing tissue pressure and increasing lymph flow. We should expect that from this equation, right? That the higher tissue pressure goes, the higher lymph flow should go. Okay, so we actually see that relationship. If we were to look at tissue pressure, okay, going from some of those negative tissue pressures that we talked about. Remember, we talked about an average tissue pressure being about -3. So if we do have some of those weird ones sitting around -6, as long as pressure in the tissue is greater than pressure in the lymph, we will get flow. So we do see that linear relationship, but then there'll be a ceiling to that. There'll be a maximum to that. Because at some point, pressure in that tissue, remember where we are, pressure in the tissue is going to become so great, it's actually going to start to become environmental pressure or transmural pressure and start to drop diameter. Okay, so you only get a certain amount, you're only going to get a maximum, there's only a peak amount of flow you're going to get with tissue pressure before you start to impinge on diameter, drop radius, increase resistance, drop flow. Okay, so that's this part, and if we were to carry it out further, indeed we could drop lymph flow depending on how high tissue pressure was. And so this is a manifestation of tissue pressure becoming high transmural pressure. Okay? So indeed, when tissue pressure is going up, we should see an increase in lymph flow. Got it. Up to this maximum, where suddenly we get an increase in tissue pressure. It goes too high. Now its effect of tissue pressure will be to decrease radius of that lymphatic. Okay, so now we're kind of up here. That environmental pressure is now so high, we're dropping radius. Right? If we start to, so it's kind of like we're becoming, that tissue pressure is now transmural pressure, high transmural pressure. Going to drop the radius of the vessels. Okay, now we're going to increase resistance. And in terms of flow equaling P1 minus P2 over R, okay, we've just increased resistance, so that's going to drop flow. Okay, and you've seen these types of diseases where folks will have decreased or increased their tissue pressure so high that it's now transmural pressure, and they have shut down their lymphatics, and they have massive swelling on the limbs. So you often see it as I think it's a parasite that lodges itself and into the lymphatics. and messes with the pressure, but as a result of that, you can't get your 3 liters a day off that piece of tissue, so it stays on. 3 liters a day on a piece of tissue is massive tissue pressure, okay? Massive tissue pressure. And at some point, that will start to interfere with all the other lymphatics in the leg, because it's acting to decrease the diameter of all the lymphatics now, increase resistance and drop flow. Now we can't take any tissue or any fluid off the tissue, okay? So you'll see people with massive edema. So it's a bad day when tissue pressure becomes transmural pressure, right? Because then we stop removing that 3 liters a day off. Okay, so those are 4 ways in which we get to help, or we are built to help promote lymph to flow. Okay, so on a good day, like right now, on a good day, we are taking off that 3 liters and lymph is flowing unobstructed back close to the right atria. And you can see why now we have to go back to the right atria. We need very low pressures. These are very low pressure systems, right? And in fact, in some cases, for pressure in the tissue to be greater than pressure in the lymph, if your tissue pressure is -4, then your lymph pressure actually has to be more negative than that. So we're talking about wicked negative pressures here. And then by the time we get up to collector lymph, very, very, very low pressures, right? Because the right atria is around 0. So the lymphatics kind of have to be around 0 pressure by the time we empty into that, or else we're not going to empty into it. Okay, so it's got to be a very low pressure system. It's crazy. I don't know how we work that, but get to grad school, figure that out. Okay, so it's a good thing. We can filter volume off into the tissue, and now we know we're fine. We can get that volume back from the tissue into the cardiovascular system. Okay, so life is good. So let's go back to our tool for looking at fluid flux across a capillary bed and see how we're going to use this, right? It's not a useful tool for us to regulate mean arterial pressure with something we can't regulate. If fluid flux was fixed at the level of the capillary, we wouldn't care at all about talking about it in regulation of mean arterial pressure, would we? If it's not something we can change, then well, who cares? Then we would just describe something, memorize it, and move on, right? But the reason we go through all this and develop a tool is because it does change. So that there will be scenarios where suddenly you are taking more volume from the blood compartment into the interstitial space. Drop in blood volume, drop in blood pressure. Okay, and then there'll be other scenarios where we do the opposite, where we take fluid from the tissue, put it back into the blood compartment, increase volume, increase pressure. Okay? Tissues are just temporary reservoirs for fluid. Okay, this is a critical piece in terms of how the body is using tissues. Tissues are reservoirs for fluid. Okay? The only other way that your body can convince you to take fluid on is to get you to drink. And that is really complicated, right? So it has reservoirs. All your skeletal muscles are really reservoirs for volume. So if the body needs some real quick, bam, I got it right there. If I need a place to put some, I'll put it there. Okay, so your tissues, especially skeletal muscle, are reservoirs for volume. Okay? So let's then look at how we either tap that reservoir or put into that reservoir. Okay? So then let's think about then the regulation of fluid flux. All right, so let's think about that regulation of capillary fluid flux. Because if we couldn't regulate it, we wouldn't be talking about it. So Let's jump off of an example that we had on the problem-solving session on Friday. So let's say, and we're just going to take these in isolated incidences, okay? We are going to build the system bigger, but right now, in order for us to flex our muscle a little bit, we just need to change one thing at a time before we change multiple things, okay? So let's change one thing. Let's say your body was responding to something, and I've got an increase in sympathetic nervous system stimulation to arterioles. Okay, so I'm sending out a vasoconstrictor signal. We don't know why the body's doing it, but we're just going to look at this piece. Okay, so if I increase SNS activation, increase SNS activation of arterioles. Okay, so when we're thinking about capillary fluid flux, there were only 4 variables that dictated it that were going to change, right? There was that constant, which we were going to forget about, capillary filtration coefficient. Other than that, there were 4 other variables. So we have to look at this and say, okay, SNS activation of arterioles, how does that affect pressure in the capillary, pressure in the tissue, osmotic pressure in the capillary, osmotic pressure in the tissue? Because if it doesn't change those 4 things, it does not change, or one of those 4 things, it does not change capillary fluid flux. Okay, so if you look at that and kind of go, nah, doesn't change any one of those 4 variables, then we don't have to worry about moving volume from the tissue into the blood space or vice versa. Okay? So can you think about then how vasoconstriction, so I'll give you that piece, vasoconstriction of arterioles would change one of those 4 variables. Okay, so vasoconstriction. Any thoughts on how we might change something about the capillaries? Because if not, if it doesn't change any of those, we can go on to example number 2. Yeah? Give it a go. Oh, brilliant. Indeed. So we go back to our modeling that capillary as a compartment, right? Because we want to know what the volume in these capillaries are and what the pressure in those capillaries are. All right, and we talked about volume in, volume out arguments. What dictates volume in? Mean arterial pressure and our resistance arterioles. Okay, what dictates volume out of this compartment? Pressure in the capillary dictates the volume out of the compartment, and venous pressure dictates volume out. That means circulatory filling pressure, venous pressure, okay? Okay. So, what we did in terms of flow into the capillary bed, let's put this on here so we're all comfy. Okay, what we did was we messed with resistance when it comes to flow into. Okay. So increasing resistance is going to drop volume into the capillary bed. And the volume out remains constant. Then we're decreasing the amount going in. The amount going out is normal, so we're going to decrease the amount in the capillary bed. Okay? So we're going to decrease volume in that capillary bed. What is that? That was our hydrostatic pressure. That was capillary pressure. Okay? All right, so we've changed one of our variables. So how does this change filtration or reabsorption? Right? And a drop in pressure. So filtration and reabsorption was a comparison of the two variables delta P and delta pi. Right? Is delta P higher or lower than delta pi? Right? So dropping pressure in the capillary, that means I'm going to drop delta pi, right? Because remember, delta pi was PC minus PT. All right, I've just dropped PC, so delta pi has to drop. Okay? So now if we use our tool and think about what that means for filtration and reabsorption, under normal conditions, we had delta P dropping across the length of the capillary bed, so we would get flow. Okay, so that was just our normal scenario. And then we had our normal delta pi. Which didn't change much across the length of the capillary bed, right? That's just the concentration, mostly due to the concentration of the proteins in the vascular space. And then, so that we're just writing down normal here. So this would result then in a normal amount of filtration that we talked about over 75% of the capillary bed, and then reabsorption over about 25% of that capillary bed. So that was just our normal scenario, okay? That's just reiterating what we talked about on Thursday. But then we've just done something here where we drop pressure in the capillary, therefore drop delta P. So delta P becomes lower. Right, so what happens when delta P becomes lower? So this is our new delta P. We've just dropped it. So what does this tell us about filtration and reabsorption? Okay, this tells us that over this much of the capillary bed, we are still filtering because delta P is greater than delta pi, right? So we're still filtering over part of the capillary bed, but it's less. So we're filtering less. Right? And now there's also a larger, we're reabsorbing still, but it's over a larger portion of this capillary bed. So over a larger region of this capillary bed, we're reabsorbing. Okay? So this tool tells us now that by dropping delta P, we are filtering less and reabsorbing more. Okay? All right, so we're filtering less, reabsorbing more. So what does that actually mean? I'm putting less fluid onto the tissues, and I'm removing more from the tissue. So more fluid then is moving from the interstitial space into the capillary bed than was before. Okay? So more fluid is moving from the tissue or that interstitial space to the capillary bed. And if it's in the capillary space now, it's blood volume, isn't it? We've just increased our blood volume. So vasoconstriction of arterioles will increase blood volume. Okay? When we move fluid from the interstitial space into the capillary lumen, we have essentially moved volume from our tissues into our blood space. So that is going to represent an increase in blood volume. Why did we care? Increase in blood volume, increase in blood pressure. Okay? We are going to relate this essentially at some point back to mean arterial pressure, but that's the link. Okay? That was the whole reason for doing the maneuver. We actually tapped into the reservoir of our tissue fluid on our tissues and managed to get it back into our blood compartment. Okay? Tissues are a reservoir for volume. Okay, we can put volume there on a milliseconds time scale. This is just physics. This is all happening on a milliseconds time scale. Okay? Milliseconds to seconds. Okay, so what does that mean? So we've got blood moving from the interstitial space into the capillary bed. So that would represent an increase in blood volume at the level of the capillary, but what does it represent in terms of the tissue? What happened to the volume in the tissue? If I move more from the interstitial space into the blood, what happened to volume in the tissue? It decreased, right? Because we put it from the interstitial space into the blood space. Perfect. So that would also then mean a decrease in volume in the tissue. Well, decrease in volume in the tissue then means that we decreased pressure in the tissue. So what just happened to lymph flow? If you drop pressure in the tissue, what happens to flow in the lymph? You start to see how everything starts to be connected. Okay? What happens to flow in the lymph? Anybody got an idea? Up? Down? It decreases, okay? Can you explain that to me? How you... I totally buy decreased lymph flow. Okay? And that basically comes from, in case you forgot, flow equals PT minus P lymph over resistance. We've just said we drop pressure in the tissue, we drop lymph flow. Okay, brilliant test question. Vasoconstrictor arterioles, what happens to lymph flow? Okay, can you see how you can get there? It becomes all connected. Okay? Someone has a question on this. We'll do more examples. Yes? No? Okay, let's give you another one to think about then. Let's talk about, it's another bad day. Let's talk about heart failure. We're just going to talk about one component of heart failure, because we will build on this as we go. Let's throw ourselves into right heart failure. So heart failure is essentially a drop in pump function, right? If we're in heart failure, that usually means something is wrong with the muscle cells of one of the ventricles, so our pump isn't pumping like it should. Okay? So at the end of the day, heart failure represents, in the right heart, is a decrease in pump function. Okay, so we're really just caring about then if change in this heart function can change pressure in the capillary, pressure in the tissue, osmotic pressure in the capillary, osmotic pressure in the tissue. If it can change one of those four variables, it can change fluid flux at the capillary. If it can't, it won't. Okay? So let's think a little bit about our circulatory system so we can see where we're at and why changing the right pump might affect one of these variables. Okay, so real quick and dirty look at our circulatory system and how different compartments might be changed. We've got volume going from our left heart into our systemic vasculature, through the capillaries back to the right heart, up to the pulmonary system, back to the left heart, blah, 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 okay? And you know an awful lot about this little model that's been put up here. You know where resistance arterioles sit. You know where mean arterial pressure is and where it's measured, et cetera, okay? So we have a decrease in pump function, which means, and what does the right heart do? The right heart takes volume from the systemic veins and puts it into the pulmonary artery. That's all that pump does, right? So that pump just takes volume from systemic veins and puts it up into the pulmonary arteries. So if the pump stops doing this, what is going to happen to volume in the systemic veins? If we stop moving volume from the systemic veins and putting it into the pulmonary artery, what happens to volume in our systemic veins? Any idea what happens to volume in the systemic veins? Any thoughts? Yes. So we're going to have a decrease in cardiac output of the right heart. That's exactly true. That's exactly what's going to happen. Where's that cardiac output going? It's going here. So if I've got a decrease in cardiac output of the right heart, that means I'm going to have a decrease in volume up here, right? Would you buy that? Okay, I'd buy that. So we'll think about that pulmonary artery compartment. I'm pumping less into it, right? So I'm going to have a decrease in volume and a decrease in pressure here. Totally buy that argument. Not sure that's really going to mess with pressure in the capillaries, though. What about that systemic vein compartment? Yeah. Perfect. So, excellent. So the answer is, since I'm pumping less and I'm removing less from this compartment, I'm going to have more in it. So I'm going to get a backup, or a backlog was the word used, of volume in the systemic veins. Okay, so we should absolutely expect an increase in volume and an increase in pressure in our systemic veins, because we're not moving volume out of that compartment, are we? Okay, increase in volume in the systemic veins, increase in pressure in the veins, increased venous pressure. Okay, we have just increased mean circulatory filling pressure. Okay. And would that affect pressure in the capillary? So I'm going to go back to the model that we put up earlier. You've just told me that mean circulatory filling pressure went up. Okay? So I'm just going to transfer this model over here. Okay, and now you've just told me that we increased mean circulatory filling pressure. So in terms of our volume in, volume out, because we don't actually, we want to know what the volume is in that capillary bed, so we know what the pressure in that capillary bed is. So in terms of our volume in, volume out argument, how does this change things? At the moment, we're going to argue that volume in is going to remain constant. Okay, so we're going to keep that piece separate. So volume in's constant. What happens to volume out of? Any thoughts? Volume out increases. Okay, so you want to work me through that. So how? Yeah. Volume decreases. Whoa, okay. So work me through that. Okay, so if this was P1 and this was P2, there you go. Okay, so to get flow out of the capillary bed, we needed a pressure drop, and suddenly we increased P2, which decreases our pressure drop. So we're going to get less volume out of, right? So if I decrease volume out of the capillary bed, if I've got the same amount coming in and I've decreased the amount going out, I've got to have an increase in volume in the capillary bed. Increase in volume in capillary bed, increased pressure in the capillary bed. How does that change delta P? Increase delta P, because delta P equals PC minus PT, and we have just increased PC. Excellent. Let's take a break, and we'll get back at solving that problem. We can talk about it after class. Okay, so is everybody comfy with what is written on this overhead right now? I mean, if you have questions, now's the time to ask them. If not, we are going to move on. So everyone is comfortable. All right, then what happens? We've got ourselves to a mean circulatory filling pressure change, and that will decrease volume out of this compartment. If volume out of is dropped, then volume in must be higher. If volume in is high, pressure's high, which increases delta P. All right, so then how does that change fluid flux across the capillary bed? So under normal circumstances, we have a pressure drop across that capillary bed. A certain amount of the capillary bed we see filtration, a certain amount we see reabsorption. Where delta P is greater than delta pi, we get filtration. Where delta pi is greater than delta P, we get reabsorption. Okay, so that was just what we were talking about in terms of our normal state. Okay, what happens with a scenario where we increase delta P? All right, so suddenly if we were to increase delta P, so that's our new delta P, that means over this length of the capillary bed we are now filtering, and over this a smaller length of the capillary bed we are reabsorbing. Okay, so what does this mean? We are filtering more, reabsorbing less. All right, that's just reading that graph. There's a larger region over which delta P is now greater than delta pi, filtering more. So what does that mean for a change in blood volume? filtering more, reabsorbing less. What does that mean for the volume in the blood compartment? We are filtering more, reabsorbing less. So blood volume goes up or down. Down. Got it. Indeed. Right, because we're putting it on the tissue. Filtering more, we're taking it from the capillary space into the tissue space, right? So we've got less in the capillary space, but what does this mean for volume in the interstitial space? What does this mean for volume in the tissue? It goes up. Perfect. Increasing that interstitial space volume, or increasing that tissue volume. And if we increase tissue volume, we're going to increase tissue pressure. Okay, how will this affect lymph flow? You're going to increase your lymph flow. Awesome. Because flow, when we're thinking about lymph, was dictated by the pressure drop between pressure in the tissue and pressure in the lymph and resistance. We didn't mess with that. We increased pressure in the tissue. Therefore, increased lymph flow. Perfect. Okay. So we can increase and decrease our delta P line. Let's make sure you leave with an example where we mess with delta pi. Okay, because as soon as you see that, then there is no question that you can't answer using this tool. Okay. So let's think about let's mess with kidney function. So then I'll just have to say that if we change, the kidney is a filter, and if we change how we filter, we're going to change our plasma proteins in the concentration of plasma proteins in our blood, because the kidney essentially filters our blood. Okay, so changing those plasma proteins. So let's say the problem is an increase excretion of plasma proteins. Okay, so we're filtering more out at the kidney. So we're losing plasma proteins from our blood space. Okay, decrease in plasma proteins in our blood space. So is this going to change pressure in the capillary, hydrostatic pressure in the capillary of the tissue, or osmotic pressure in the capillary of the tissue? Because if it changes one of those four, we're going to change filtration or fluid flux at the capillary. If it doesn't change one of those four, then we don't have to worry about what's going to happen with fluid flux. So what variable is this messing with? Is it messing with hydrostatic pressure? Let's do process of elimination. Is it messing with hydrostatic pressure? No? Perfect. It's not messing with PC. Is it messing with pressure in the tissue? No, because that's even the wrong compartment. Is it messing with osmolarity in the capillary? Is it messing with osmolarity in the tissue? It's going to mess with osmolarity in the capillary. That's right, because that's what pi c was, right? And you're absolutely right. So I'm going to decrease pi c. All right, so then how does this change in terms of capillary fluid flux? We want to know the relative difference between delta p and delta pi. How is this going to change delta pi? Okay, if we look back, at what delta pi was, how is a decrease in pi c going to change delta pi? It's what, sorry? It's going to decrease delta p, or delta pi. I would buy that. Yes, decrease delta pi, because delta pi was equal to pi c minus pi t, right? And we just decreased pi c, so indeed delta pi has to go down. Awesome. So now we have to look at the relative difference between delta p and delta pi. So under our normal scenario, over 3/4 of the capillary bed, we have delta P being greater than delta pi, so we're filtering. And about 1/4 of the capillary bed, delta pi is greater than delta P. So we're absorbing. Okay, that's just our normal scenario. And now our delta pi has dropped. That's our new delta pi. Okay, so we've dropped our delta pi line. Now we have a larger region over which delta p is greater than delta pi, so we're filtering. Over a larger region and a smaller region in which delta pi is greater than delta p. So a smaller region we are reabsorbing. Okay, so what does this mean? This just says we're increasing our filtration and decreasing our reabsorption, right? Increasing filtration, decreasing reabsorption. So what is happening with blood volume? Increasing filtration, decreasing reabsorption. What's happening with blood volume? Up or down? Up or down? What are we thinking? Yep. It's going to increase. Okay? Make sense? Yeah? This? No, I cannot explain that. It doesn't make sense to you? Well, then explain the other way. Give it a go. Increased filtration is moving blood from what compartment? To what compartment? I just put up here what I'm told. We can move on, but if you don't agree with it, argue with me. Yeah. Perfect. Okay. So we are exactly. We are filtering. What does that word mean? Moving volume from the blood compartment into the interstitial space. I'm filtering more. I'm moving more volume from the blood compartment to the interstitial space. Okay, which means there has to be less there in the blood compartment then. Got it? You said decrease? Yeah. And I messed with you? Good teaching moment then. Thank you. We'll have to get hand signals. Decrease, increase, decrease blood volume. Nice. Which means we have more on the tissue, right? Which means we have an increase then in volume on the interstitial space. Which means we have an increase in pressure in the tissue. Okay, and what's going to happen with lymph flow with an increase in pressure in the tissue? Increase or decrease? Point in, thank you. Increase lymph flow, nice. Okay, so we can move both lines. You can also move both lines at the same time. Okay, we move one line at a time. So for now that you're all big and bad, but moving your lines, I want you to do this one. The situation of dehydration. Okay, dehydration is a volume loss, so lots of sweating. Okay, so it's a volume loss. And so there's going to be a decrease in blood volume because of that dehydration, but it was just volume loss. You didn't lose plasma proteins, you just lost volume. Okay, so you will have an increase in concentration of plasma proteins. Okay? So you should totally be able to do that one. And I'll leave that one with you. Okay, we'll cut it there.